Hey, so welcome to the plane curves class today. We are currently discussing divisor class groups. We just introduced divisor classes at the end of last section, last lecture. So let me quickly recall what this was. So we always talked about smooth projective curves. So F could be, so smooth is always understood here now, a projective curve over an algebraically closed field, which is also a general assumption here. And then we had defined the following groups. First of all, the groups of all divisors. This was at the beginning of last lecture. So div F is the group of divisors on F, where a divisor is a finite formal linear combination of points with integer coefficients. So you can write it as A1, P1 plus A and Pn, where the AI are integers and Pi are points on the curve. In other words, it's the free abelian group generated by the points on the curve. So we had inside there the subgroup div 0F. These were divisors of degree 0. That means where the sum of the AI is 0. And this group is, so rather, I mean, from the structure, rather uninteresting because it's a free group and it's also very big. So the way around this to make some interesting structure from that is to take a quotient group modulo the subgroup of principal divisors. So we defined principal divisors. This was prin F, the subgroup of all divisors of the form, the divisor of a rational function. So div phi, where phi is a rational function and on 0, 1. And this div phi was defined to be the formal sum over all points on the curve. And then each point occurs with the multiplicity in that function. So we had seen that this is a subgroup of div F and also of div 0 of F. That's basically because this divisor map is a group homomorphism from Kf star to the integer to the group of divisors. And hence we get a subgroup here. So it's just the image group. And then we define the Picard group or divisor class group as pic F as the quotient. So div F modulo prin F divisors modulo principal divisors, or a degree 0 version pic 0 F is div 0 F mod prin F. So these are called divisor class groups or Picard group. So that's what we did at the end of last lecture. And first of all, the difference between those two is rather small. It depends on the application in mind, which one we're looking at. Namely, the quotient of the two is basically just the integers because there's the degree map. So the degree map induces an isomorphism by the homomorphism theorem between, well, if you do it for divisors, we can take div F mod div 0F, because the degree map is a homomorphism on the divisors and it maps to the integers. And the kernel of that is by definition the degree 0 divisor. So that means that quotient is just the integers. And in the same way, we have that the Picard group of F modulo the Picard 0 group of F is just isomorphic to the integers by the homomorphism theorem. And that means that the two groups, so div F or div 0F, respectively, div pic F and pic 0F, carry more or less the same information. So they fit into an exact sequence with the integers. So if we want to study the structure of the group, it doesn't really matter which one we take. So sometimes we take this and sometimes we take that one. So say pic 0 or pic F and pic 0F carry essentially the same information about the curve. So we'll take sometimes that and sometimes the other, pretty much the same group. Let's start with some examples maybe, and start with curves of low degrees. Namely, start with degree 1. So say if f is a line, so degree 1, then I claim that this group is actually trivial. And the reason for that is quite simple. So if we have any point P on F, so P on F, there's obviously a line through that point that is not F. We just pick any. Let me call this LP, so line through P, not equal to F through P. And that means that the divisor of that line on F is just that one point. So the line intersects F in this one point. And that means the divisor of LP is just P. Like the intersection multiplicity is 1. So we can do that for any point, but that means if we have any 2 points, P and Q, we can form the quotient LP over LQ, which is a rational function. It's the quotient of 2 homogeneous polynomials of the same degree, and the divisor is P minus Q. So the divisor of LP over LQ, which is a rational function, a non-zero one, is obviously P minus Q. And that means that is a principal divisor, so we mod this out. So P minus Q is in print F, which means that the class of P is the same as the class of Q, or they are equivalent. So let me write this with the equivalent sign. So as divisors. Or maybe I should say this here as well. So we've introduced the notation for the classes of that, or the equivalence relation there induced by that. So this is here, this is divisor class group. So if, say, the classes are the same, so D1 and D2 are the same class, and pick F, we write D1 equivalent to D2, and usually it's just called linear equivalence, so they are called linearly equivalent divisors. That just means they are the same divisor class, they are the same in the Picard group. And that means any 2 points are the same. And that means, for example, if we have the Picard group pick 0, then any element in this of pick 0F is of the form so D, and then we have a couple of positive points, P1 up to PM, and then a couple of negative points. So some of the points might be the same. It's just so I omit the multiplicities because they we can have a point occurring multiple times in there. But in any case, if the degree is 0, we must have equally many points with a plus and with a minus. And of course, we can write this then as P1 minus Q1 plus and so on, PM minus QM. And each of these difference of 2 points is 0 because they're equivalent. So this here is equivalent to 0, and this is equivalent to 0. So the whole thing is equivalent to 0. So every divisor of degree 0 is equivalent to 0. So that means the Picard group pick 0 is trivial. Which would mean by that the Picard group itself is the integers and just given by the degree. So I pick F is isomorphic to the integers by the degree homomorphic. So that's a very simple situation. In that case, we've modded out so much that the resulting group is trivial. But then a line is not so interesting, actually. So case B, let's go to the next degree, degree 2, a conic. And there we actually have the same. Let's say F a conic. That means the degree of F is 2. There we see on the current homework sheet, it was on 2B, I think. that the same thing here holds as well. So I hadn't introduced like this principal divisors at that point, but that we show that there is a rational function whose divisor is p minus q. So by homework 5.2b, there is again, for any 2 points, p and q and f, a rational function whose divisor is p minus q. So the same argument as above holds, right? So in any divisor of degree 0, you can write it in that form. You just pair it in groups of 2 with a plus and a minus, and each of them is 0. So you get again that the Picard group is 0 as above. Again, pick 0f is trivial as above. And hence, again, pick f would be the integers as above. So these two cases are easy and trivial. And again, maybe I've said this before. So the main reason behind that is that if we had talked about isomorphism between curves as abstract curves, then a degree 2 curve would actually be isomorphic to that one. And hence we get the same result. But we haven't done that. So, well, that's just an observation here. However, this group is not always trivial. I guess otherwise you wouldn't have introduced it. Rather, starting from degree 3 of the curves, it starts to get interesting. And the first result in that direction is our first proposition today, which says that for curves of degree 3, okay, however, the proposition is just the very first result in that direction. So say let f be a projective curve of degree at least 3. Then if we take any 2 points, they would never be rationally linearly equivalent, actually. So that means p minus q is never 0 in the Picard group, and in particular, the Picard group will not be trivial. Then for any distinct p and q and f, we have that p is not equivalent to q and pick f. And in particular, this means that the Picard group pick 0 is not trivial. So could also write p minus q is not 0 in the Picard group pick 0f, i.e. pick 0f is not isomorphic to the trivial group. And let's show that. So that already uses some of the results that we considered, that we had so far. So it's not an easy statement, but we've done enough preparations to be able to prove that now. So let us actually start with 2 points, p and q, such that they are linearly equivalent, and then we will show that p is q. So say let p and q and f such that p is linear equivalent to q. And that means we have a rational function phi as there. We just don't know whether it's a quotient of lines. It's any rational function whose divisor is p minus q. So there is a phi rational function. We can write it as f over b, of course, as usual, with quotients of homogeneous polynomials of the same degree, such that the divisor of phi, which is the divisor of f minus the divisor of g, is p minus q. So what we do then is we pick again a line as before. So LQ, let me call this. It's a line through Q. Otherwise, we don't need anything about this. So as before, that LQ be a line through Q. So then let's compute the following. We'll just multiply f with this line and compute its divisor. So the divisor of f times LQ is then what? So the divisor is additive. So that means that's div f plus div LQ. And so the divisors of f are right as the divisor of f over g plus the divisor of g, which works for the same reason. Divisor is additive. So let me rewrite this as div f minus div g plus div g plus div LQ. And let's look at the individual terms. So div f minus div g was p minus q. So that is just p minus q. The divisor of g is just something. It's an effective divisor, so it contains only points with positive multiplicities, as it's a polynomial and not a rational function. And this LQ here is a line through Q. But in comparison to the line case here, the divisor is of course not just Q, but the line will intersect the curve in D points. And Q is just one of them. So that means we can write this divisor as Q plus D minus one more points. And I write this as E for effective divisor. So this is any effective divisor of degree D minus 1 containing the other intersection points, which might coincide, right? I mean, so depending if the line is tangent to some other points, it might be that points occur there with multiples, but it's degree D minus 1. Any effective divisor of degree D minus 1 containing the other intersection points. So that's how we can write this. And the main thing that happens here is that the minus q here cancels, right, by the plus q. So that means we get a p plus the divisor of g and then plus e. So that is now an effective divisor, right? So all the minuses were gone. The only minus that we knew about was the minus q. So this is an effective divisor. And in particular, it's greater or equal to div g. All right, so we just leave out p and we leave out the effective divisor here. And then we have Max-Noether's theorem, and that's the one point where something non-trivial comes in, where we had seen that if the divisor of one homogeneous polynomial is less than or equal to the divisor of another homogeneous polynomial, then the remaining divisor comes also from a polynomial. That was Max-Noether's theorem raised for divisors. And Max-Noether's theorem there is another homogeneous polynomial such that makes up the difference, so such that the divisor of g plus the other divisor of the other polynomial is div of f times LQ. And what is the degree? I mean, obviously it has to be a line because the degree of f is the same as that of g, and there's a line here, so by Bezout we need a line here as well. By Max-Noether's theorem, there is a line L such that that makes the difference, so such that div of f LQ is div of GL. That means that the divisor of L is just those things here, p plus e, the things we left out, i.e. the divisor of L is p plus e. And as I said, so this is the one point in the proof where something non-trivial comes in. If we compare now this line to that line, then we see that this point P and Q is different here, but they both contain the other D minus 1 points, which are in E. And as the degree of the curve is at least 3, this means D minus 1 is at least 2. So there's at least 2 points here in E, and both lines pass through these 2 points. And that means they must be the same line. Right? A line is uniquely determined by 2 points. Even if the 2 points should be the same, it must be the tangent to the curve at this point, which is also unique. So in any case, the line is the same as that one. And if the line is the same, then the point is the same. Right? So P must be equal to Q. So write this down. So now both L and LQ pass through the D minus 1 points of E, and D minus 1 is at least 2, so that's what we need. D is at least 3. And hence they must be the same line. So that means L is LQ, and hence also the divisors are the same, and so that means P is equal to. That shows the statement here. Right? So there we also see why we need degree at least 3. So if the degree was only 2 or less, then E would contain fewer than 2 points, and that wouldn't determine the line, and so we could have 2 different lines. Right, so that means starting from degree 3, the Picard group, even pick 0, will definitely be non-trivial, and we will see more about the structure in the next chapter. So in fact, it's a very interesting group in general, and the first thing that we can follow from that is a corollary, which is a map that we will also consider in the next chapter, in particular for degree 3, is namely that, again, let F be a curve of degree at least 3. Then the map, let me call this here capital Phi, it goes from the points of F to the Picard group, pick 0 of F, should actually pick a base point. So then for a given base point, P0 in F, and then the map. So from V of F to pick 0 of F, which sends any point P to P minus P0. Right, so P minus P0, so the minus is the minus in the Picard group, so that means we have one positive, one negative point that has degree 0. So it lands in pick 0, and this is injective. So that means we sort of have an embedding of the points of the curve in its degree 0 Picard group. Well, embedding just in the sense of injective map, but it's already something that we can see starts to get very interesting, because a priori this V of F is a variety, so it's the structure we are talking about here in class. And pick 0 of F is just a group. Okay? And just to start with, V of F is not a group and pick 0 of F is not a variety, but still we have an injective map like between totally different categories, let's say. What is the proof here? That really just follows from that. Namely, so obviously we have a well-defined map there. And if the result is the same, so if phi of P equals phi of Q, then that would mean that P minus P0 is Q minus P0 in the Picard group, which would mean that these are linearly equivalent divisors, so P minus P0 is equivalent to Q minus P0, which means that P is equivalent to Q, and that we have just seen by our proposition means that P is equal to Q. So that's just a very simple consequence of that proposition that we had before, so we can embed, at least have a map, or no structure at the moment, just an injective map between the curve and its degree 0 Picard group. So any questions about it? Okay. So that means in terms of this Picard group, the degree 3 case is the first interesting case where something happens. And so actually I want to take a whole chapter on studying these curves. So these curves of degree 3 are called elliptic curves. And that's the content of the next chapter. So which is chapter 7. So the definition is just to start right away with it. It's just a different name for projective curves of degree 3. So an elliptic curve is a projective curve of degree 3. And as of our conventions, it always means here, of course, smooth and over an algebraically closed field. And that's what we want to study here. So we've seen a couple of cases now already here in class where degree 3 curves were the first cases where something interesting happens. Right? I mean, so in our application of Bézout's theorem chapter, we had, for example, the topological statements. So we studied how many loops can a real projective curve have, or what are the number of holes of a complex projective curve. Now here we have the Picard group. And in each of these cases, degree 3 curves were the first case where something interesting happened. And so that's what we want to look at now. Actually, just one remark. The name elliptic curve is probably a bit confusing. So, I mean, the curves don't look like an ellipse. I mean, an ellipse would be a degree 2 curve after all. So, and the name just comes from, I mean, there's maybe a term, elliptic integrals, that you might have heard. So they are related to that one. Or what that actually comes from, if you take an ellipse and want to compute the circumference of an ellipse, well, that's somehow complicated. I mean, it's only possible to it's not possible to compute this directly in explicit terms, but you can write it down in terms of an integral over such a curve here, and that's why it's called an elliptic curve. So that's just a remark about the name. So don't think, please, it's an ellipse. It's just a curve of degree 3. Instead, the standard real picture would be, well, could be something like this. So that would be a degree 3 curve over the reals. Or we had also seen a disconnected one, or something like that. That could be an elliptic curve over the real numbers, I mean, if you draw a real picture. And so these elliptic curves, so the main feature of them, as we will see here, is that they have a group structure on them. We'll see the main feature of them is they have a group structure, which varieties, of course, usually don't have, curves don't have, but in that case they do. And the reason is just that it will turn out that this map up there, so this map phi, is, in the case of elliptic curves, actually a bijection. So that means we can really identify the points of the curve with the Picard group, and that is a group. And that will give us a group structure. So the idea for that is the following. So for this, we need the following construction. We need to use divisors. And the degree 3 case is special in that sense that it allows us to define an operation on the set of all points on the curve. Namely, if we take any 2 points on the curve, then we could take the line through them, or in the case of the same point twice, we take the tangent. And as we have the cubic now, so a curve of degree 3, that line will intersect the curve in exactly one more point by Bézout. And this curve will then be the result of the operation. So let me give this construction here. So maybe draw a picture here. That might be a picture of the curve. To say let f be an elliptic curve. And then we have 2 points, P and Q and F. So say there's a point P here, there's a point Q here. Then there is a unique line through the 2 points, or if we have P equals Q, we will have to take the tangent. In any case, it means that the divisor of the line will contain P plus Q. That will be the correct way to phrase it in both cases. So then there is a unique line, so in the same way as in the proof that we just had. Line L through P and Q. So that means in the sense that the divisor of L is greater or equal to P plus Q. So that would also be correct. If P equals Q, then it means that the divisor is at least 2P, so there must be have the tangent. In the case P equals Q, we must have the tangent. And now if we take the line through P and Q, it will intersect the curve in one more point. And this point we call, let me just call it psi of P and Q. So that's an operation that we can define on the curve. We define psi of P and Q, that will also be a point of F as the third point of intersection. So i.e., again, in the correct way of writing this, even if we have multiplicities and some of the points are inside, i.e., we have the divisor of L is P plus Q plus this point psi of PQ. Right? So that would be the correct way of saying that. And that we can always do, even if points coincide. So that means that is so the psi is therefore a function that takes 2 points of the curve and gives us a third point. And that is the construction. And that we will use now to construct this group structure, or respectively show that the Picard group is actually bijective to the curve. There's one preliminary lemma that we will need a couple of times, so let me start with that. So lemma is the following. So again, let F be an elliptic curve, as always in this chapter. And say we have 3 points on it, so P, Q, and R, and F. So then the statement is, then there is a fourth point, so then there is a point S and F such that the divisor P plus Q is linearly equivalent to R plus S. So that means they are the same element in the Picard group. And we can even say what S is, namely, we can take for S the following construction. We take psi of P and Q and then R. So that means the construction is you take the points P and Q, take the unique line through P and Q, it will intersect it in another point, and you take this point and R, there's again a unique line, and the third intersection point will be this S. And that point, as I claim, satisfies that relation, and that we'll need a couple of times, so let me put it before in the lemma, and then you can also see how to construct this point actually. So geometrically, if you want to, say, if you have a picture. So the proof is as follows. It's quite simple. We can write down explicitly a rational function that gives us this linear equivalence, namely. So first of all, let L be the line through P and Q. So in the same way as above, so that means we take the tangent to the point if the points are the same. And that means, as up there, the divisor of L will be P plus Q plus psi of P and Q. Now take another line, L prime, and that should be the line through the points. First of all, that one, I PQ, that's the point on the curve. We take that one and R. And that means the divisor of L prime will be the first point, psi PQ, plus the second point, plus the psi of the first with the second. So psi of PQ and R. So same thing as up there. And we just take the rational function that is the quotient of these two lines. So divisor of L over L prime, so that is a rational function, non-zero rational function, is then this minus that, and we see that the psi PQ just cancels out, and we get a P plus Q minus R minus this psi PQ R. And if we call that point S here, then that means this is 0 in the Picard group, and that is exactly the relation that we want. So that is now P plus Q minus R minus S. So this is equivalent to 0. And that means P plus Q equivalent to R plus S. So we're just using that construction here twice, right? For in such a way that this point psi of P and Q cancels, and hence we get this double psi. That result we can now use to show that our map phi that we have just introduced, the set theoretic map between the points of a curve and the degree 0 Picard group, is a bijection for elliptic curves. So that's a proposition or corollary. I mean, it is sort of a corollary, but it's so important. Yeah, I call it a proposition. Okay. Proposition is as follows. So for any elliptic curve f, and chosen base point P0 in F, the map that we had before. I'm going to write it down again. So phi from the points of F to the degree 0 Picard group, which sends the point P to P minus P0, is actually a bijection. And we know already it's injective, so that means you have to show it's surjective. So injective we've shown already at the end of last section. So let's talk about surjectivity. And that means we have to start with any divisor of degree 0. Let D be any divisor of degree 0, because we start in the degree 0 Picard group. So we can write it as before, as D is P1 plus P2 plus and so on, Pm minus Q1 minus up to Qm. And we want to write this up to linear equivalence in a simpler way, namely we must be able to write it in the form P minus P0, right? Then it's in the image of this map. So first of all, we have to get rid of a couple of points there. So the first step is, as long as there is more than one positive point in there, so as long as m is greater or equal to 2, we apply this lemma here for the points P1, P2, and Q1. And find a fourth point S such that P1 plus P2 is the same in the Picard group as Q1 plus S. So by the lemma, we find a point S in F such that P1 plus P2 is linearly equivalent to Q1 plus S, and plug this in there. Right? That means up to equivalence, P1 plus P2 minus Q1 is the same as S, so we can just cancel P1, P2, and minus Q1 and just write an S instead. So that means our divisor is linearly equivalent to S plus P3 plus and so on Pn. And then minus, so Q1 is also gone, Q2 minus Qn. And that is now a representation of the same divisor class that uses one positive point less than before. Right? And as long as we have at least two of them, we can apply this procedure. And so at the end of the first step, we'll arrive at a representation of the divisor class as just a difference of 2 points, just a P minus Q. That means we really don't need as many points as there, but one positive and one negative point is sufficient. That means we can write P as equivalent to, say, just the P1 minus Q1, or say, let me just say P minus Q, because it's not the P1 and Q1 from there. So we can just have a difference of 2 points. Well, that's not sufficient because we want the minus point there to be P0, and here it's just any. Right? So that means we have in the second step to apply our lemma again. So again, by the lemma, we find the point T now such that, and what we want now is that P plus P0, so our base point that we want to have there, is linearly equivalent to Q plus T. Right, so we have 3 given points, so the P and Q in the divisor, and a P0 that we want, and then there will be a point T like that. And that, of course, means if we just bring P minus Q to one side, that D is linearly equivalent to P minus Q. And P minus Q is T minus P0, and that is in the image of phi. And that shows that the map is actually surjective. Every divisor, so another equivalent statement would be any divisor class of degree 0 can be written in the form P minus P0 for a fixed P0. So that's the statement here. That means that we have this bijection. And as I said before, so the remark is now that this is a very interesting statement because it gives a natural bijection, well, natural up to choosing a base point, but other than that, it's a natural bijection between objects of 2 completely different categories. Right? So one is a plane curve and the other is a group. And none of them looks like it would be the other kind of type. Note. This gives a natural bijection between curve, so like a variety, one-dimensional variety, that name as we've introduced it, and the group. And so that's very special, of course, and we'll use this to define actually the structure of a group on the curve. And if we want to, we could also define the structure of a curve on the Picard group. And I mean, we can just transfer that. So we can use this to define a group structure on the points on the set of points on V of F, or of a curve on the Picard group. And both makes a lot of sense, and we could use that to our advantage. And in this class, however, we only want to focus on the first part. Because, well, I mean, as we are talking here only about plane curves, it's a bit not quite obvious to see why it should be naturally a plane curve, and also for higher degree. Let me just write it down. So here we only take the first thing. So we want to consider V of f, so the set of points as a group. And that's essentially by using the map phi. So we'll sort of require the map phi to be an isomorphism of groups. And that defines the group structure. In this class, only we consider the group structure on the set of points on the elliptic curve, which is, let me just put this in bracket, defined such that phi becomes an isomorphism of groups. So that requirement essentially defines the group structure. And so if we want to add 2 points in the group structure, it's actually in the Abelian group of, say, adding, right? Because the Picard group is in a Abelian group. So I could write this here, Abelian group structure, if you want. So that means if we want to add 2 points on the curve, at the moment we would just say, well, we translate it to the divisor. So we take P minus P0 and Q minus P0. We add the divisors as divisors, and then we know the resulting divisor we could write as some other point minus P0, and this other point will be the result. So that's the definition here. But the other thing is clearly also useful. So we could also define, consider this Pig0 as a variety. We just won't do it here. Actually, just as a remark, so this is very special to degree 3. So the bijection will not hold in that case in other degrees, of course. And but one can show, however, that the second statement, that the Picard group is a curve or variety, that is actually true for any degree. So one could make the Picard 0 group into a variety which would have higher dimension. It's no longer a curve for other curves as well. But the group structure on the curve is really special. Just a remark for higher degrees. Of f. So in fact, Pig0f is always a variety, but not a curve. So one can always do that, and in algebraic geometry one does this a lot to study these divisors. So because one can then use again algebraic geometry on this Picard group to do something useful with that. However, V of f is not a group then. So the group structure is really very special to the degree 3 case, but the other would still be true. So, as I said, so the way to compute this group operation on V of f would just be to transfer it to the other side, add the divisors, and then transfer it back. But there's actually a nicer way of doing this construction geometrically. And let's just consider that. So the construction, so what does it look like? What is the geometric construction of the group structure on V of f? Because there's actually a nice way to construct this. And yeah, And so what does it look like? So for that, to write this down, give this a specific name. So denote group structure on V of F by, so I write it with this plus with a circle around it. That is just because the ordinary plus, if we write P plus Q, that looks like divisors. And we want to, just to avoid confusion, take a different symbol for that. And correspondingly, I will denote the inverse by minus with a circle around it. So we just need a name for the for that group operation on V of F. That doesn't look like an addition of divisors. So then we can actually give an explicit construction that tells us what the sum of 2 points is. And that works as follows. So we can actually just compute this by just from the requirement that this phi is an isomorphism. So then, for any P and Q and V of F, and F, if you want, then first of all, so what is P plus Q? So that means the group structure, so in the group structure on the curve. So as we said, as we've defined it, what we do is just we take the image of that, so we take phi of that, then we add the divisors, and we take phi. So we take phi of that, then add the divisors, and then take phi of minus 1. So that means that this, by definition, this is phi to the minus 1 of phi of P plus phi of Q. So that's how we define it, right? Transfer to the other side, add the divisors, transfer back. So what is phi of P? You can just plug that in. Phi of P is P minus P0, and that is Q minus P0. So now we apply our lemma again. Namely, we saw that, and that for the points P and Q and P0. So I'm going to put this here. So lemma for P and Q and P0 that told us that there is a fourth point, which we called S there. And we could actually say what S was. Namely, it was psi of P and Q, comma P0, such that P plus Q is linearly equivalent to P0 plus S. Right? That was the lemma. And we apply that to replace this P, this Q, and this minus P0. Because P plus Q minus P0 is just S. So, and here we only need the divisor class, right? Because phi goes to the pK group, so we can replace the divisor by an equivalent one. So in the brackets here, I replace these 3 points by this 1 point S, which is, just write what it is. So it is psi of P and Q, comma P0, minus P0. And luckily enough, the divisor here is already in the form so that we can see what psi to the minus 1 is, namely this thing at the front. So this is psi of PQ P0. So that here is the formula for the addition of points on the curve. And what does it mean? There was the very geometric construction. So let's draw an elliptic curve, a real one, for example, like this. So that means we have, I don't know where I land. So here we take 2 points, P and Q. And then, then we have chosen any base point, P0, which is fixed for the group structure. And then the P plus Q, in that sense, we get by first you take the psi of PQ. So that means we take the line through P and Q. You get the third point of intersection. So this will be psi of P and Q. And then we will take the line through this point and P0. And we'll get a third point of intersection, which now is here. and that is this point P plus Q. So that's the way to compute geometrically the addition of 2 points in an elliptic curve. Draw a line through the 2 points, you'll hit the third point, then take this point and the chosen base point. Again, the line through that, you'll hit the third point, and that's the P. So I don't know if you have you seen this group structure on elliptic curve somewhere before, because it is also, I know, introduced in the cryptography class, for example. We'll see, like, I mean, it's very useful for cryptography. And you can, of course, define that completely elementary, right? By that, I mean, just to define that structure P plus Q, you just need to know that any line intersects the cubic in 3 points. I mean, that's not very hard. That's just the cubic polynomial has 3 zeros over an algebraically closed field. So you could just define that group structure. You can define that operation here, but to show that it's a group structure is quite hard if you don't come from divisors. So it's some messy, I mean, there's a way to do that, but in particular, the associativity actually is hard. Because if you try to, I mean, if you imagine you now have a third point R, and then you add this to R and then do the same construction again, or do it first with Q and R, then you get lots of lines in there and you don't see much anymore. So the more structural way to obtain this is actually using the Picard group and noting that the Picard group is bijective to the points on the curve. So let's maybe also check what inverses are. Of course, the neutral element would just be P0, because that's clear, right? Because that's the thing that maps to 0. The group structure. But let's now check what the inverse is. So what is minus P? And first of all, we can start the same as before. So minus P will be defined by first translate it to the other side where we know what the minus is, and then take the minus and then transfer it back. So in order for phi to be an isomorphism, this will be phi to the minus 1 of minus phi of P. It's here. And phi of P again is P minus P0. So minus phi of P is P0 minus P. I want to do the same trick as here with the lemma. So I just add artificially another point. So add a 0 here by adding another P0. So make this P0 plus P0 minus P minus P0. That would be the same. And then I apply the same as here. Now I find a point S such that P plus P0 is equivalent to P plus S. And it says like P0 plus P0 is equivalent to P plus S for, and then for S we need psi of P0, P0, comma P. Right? Same as here. Then we get I to the minus 1 of S minus P0. And as here, just that the point S is right what it is. I to the minus 1 of psi of P0, P0, comma P, minus P0. And that we can see that the inverse image is namely this point psi of P0, P0, comma P. So it is a construction. You see that it occurs always and always again. So just with different points. So that means to construct the inverse in that group structure. Same picture as before. P0 somewhere. Point P is somewhere. So what do we do? First of all, we have to take the line through P0 in itself, which means the tangent to P0. That's this one here. And then we got phi of P0, P0. And then we take the line to that point and P. And the point that we get as the third point of intersection Like this one would be minus b. So that's the geometric way to construct the inverse in the group structure. So that means there is a geometric construction to do that. However, it looks quite, I don't know, maybe unnatural or hard to predict what happens, right? I mean, it's not like a standard addition, but some weird constructions. And I guess you can see that if you wanted to prove that this is a group structure, it's sort of hard. I mean, it's obviously an operation on the points of the curve, but that it's a group structure is not clear. We know that now from our study of devices. As I want to apply also that group structure in some like practical cases, and let's say so cryptography is a field where this is used a lot. Let me just make a remark about the ground field, because if I want to implement that on a computer, for example, it would be sort of bad that we need an algebraically closed field, right? Because that has always infinitely many elements and that cannot store this in the computer. So what about other ground fields? And luckily enough, although we used algebraically closed fields in a lot of results up to the point here, the result that the points form a group structure is true for an arbitrary field. And actually you could sort of see, and I mean, here I draw, for example, I drew a real picture and that didn't hurt, right? So it still worked. And in fact, that's always true. And that's a remark about like this group structure over non-algebraically closed fields. Basically, the upshot would be that exists as well. And so let's come from the thing that we know. So say let K be an algebraically closed field. And K prime, say, a subfield, which is not necessarily algebraically closed. So think of the real numbers and the complex numbers, or just think of any field K prime and take for K the algebraic closure, for example. Right? So that always exists for any K prime that I want. So then assume then that you have a cubic curve that is defined over K prime, so over the small field. So now let F, so that would be now in K prime, X, Y, Z be an elliptic curve defined over K prime. Then this is in fact also in K, X, Y, Z. That means that the points of, so the K valued points of F will form the group just as we did that, right? So then we know by what we did. The K points, so let me denote that here by V of F, form a group as above. Now the K prime points, so the points that have value, I mean, where all the coordinates are in K prime, form clearly a subset of those points. And I claim that that is actually a subgroup of V of F. And so that means that the group structure just carries over also to the subfield. And we have this over an arbitrary field and not just over an algebraically closed one. And that by the same construction. So it's really just a subgroup. So the group operation is absolutely the same. Then the K prime points So let me write this as, so that is V of F intersect P2 over K prime. So it's all the points where all three coordinates are in K prime. Form for R a subgroup. And why is that? So for that, look at our basic construction. So the psi of P comma Q of V of F. Why is that? So consider our construction of psi P and Q, which was the basis for all, like for both the group structure and also the inverses, and assume that the 2 points P and Q are defined over K prime. So assume P and Q are points and V of F intersect P2 K prime. So they are defined over K prime. Then to get the point psi PQ, what we do is we take the line through the points and take the third point of intersection. But for a cubic polynomial, actually the sum of the three zeros is one way to, well, that's one way to say this. Or another way of saying this is the following. So that means if we restrict the cubic curve to the line through the points, it will be a cubic polynomial. And we know already that it has two zeros over K prime, enemy P and Q. And then the third will also be over K prime. And so that's one way of saying that. Another way of saying that is, if you think about this computationally, would be, that's what I wanted to say, is that of a cubic polynomial, the quadratic term is the sum of all the zeros. You can see that when you multiply it out. And that means in particular that when two of the zeros lie in some subfield, then the third one will as well. Then apply EQ was constructed by take the line through P and Q, which is as P and Q are defined over K prime. The equation for the line will be defined over K prime. And then they restrict the cubic F to the line to get a cubic polynomial in one variable again over K prime, because F has coefficients in K prime and the line has coefficients in K prime. So if you plug it in, you get a cubic equation over K prime. So now, as this cubic has two zeros over K prime, namely P and Q, the third zero must also be in K prime, namely the cubic is a product of three linear factors. Over K prime. And so that means that the main result that we have obtained, namely that V of F is a group with the, not with the Picard group element, with the Picard group argument, but that with the geometric operations like that this is a group is still true for an arbitrary field. And that means for applications, you could take for example, the real numbers, but more importantly for computers to implement it, you could take finite fields. So that means V of F as the group structure. As in the geometric construction above. Also for example, the real numbers of finite fields. And so as I said, so one important application of that is cryptography. And so if you went to a cryptography class, you will most definitely hear that, because it is one of the major cryptographic procedures that one knows nowadays. It's used in a lot of, I mean, it's used in the real world, like in whatever, I think Signal uses it, WhatsApp uses it, many websites use that. And that is the following remark. That's usually called elliptic curve cryptography. And that can be used for secure communication between two persons who've never met before. So that's the main goal. Is you want to have secure communication between two persons. I guess in cryptography they're always called Alice and Bob, who haven't met before. So I haven't met before just means that they weren't able to exchange a secret key. I mean, if we meet before, I can just obviously agree on a secret key, like a password or something that we can use to add to the message to get something scrambled, and then we can later decipher it. But if we've never met before, like we visit a website or so, and there was no way to exchange some secret information before, then this is the way of doing that. And so how does that work? We're using elliptic curves, and in the following way. So how to do that with elliptic curves? We do the following. So we pick publicly, everybody can know that, a lot of data. And then you will pick a ground field, which might be a finite field, and for applications it will be a finite field. Okay, so no, needn't be algebraically closed an elliptic curve. Yeah. And we pick a base point P0 and a starting point P. So both will be points in F. So there we all pick, and that's known. So both Alice and Bob may know that, and everybody else may know that as well. And of course, as usual, for cryptographic applications, the idea is always to pick somewhat complicated examples. That means the ground field will be a huge finite field. I can just give you an example later which numbers are actually used. Funnily enough, as I said, I mean, it's used on many websites, for many messengers used nowadays. They pretty much all use the same data here. So it's not even necessary to switch that to other values. So they all take the same field and the same curve. I'll tell you later what it is. But just see what's the procedure. So what is the idea behind the whole thing? Let's start with that. Now, if we take a natural number, for n and n, we can add, so first of all, the base point together with f defines the group structure on V of f, and we can add the point P to itself n times. So for n and n, the point, so n, that we write this in accordance with the other notation with the dot and the circle, so that by that I mean P plus and so on plus P n times. And also think of that number n to be huge. This point is actually easy to compute, even for large n, namely in log n time. I don't know if you've seen that before. That's just a general idea. Namely, as you have a group structure, I can regroup these additions as I like. In particular, I can first add to P to itself, then add this to itself, then this to itself, and this to itself. And so I compute 2P, 4P, 8P, 16P, and so on. And then for my n, I write down a binary expression and just add the corresponding powers of 2 times P. And so then I've used log n times. So that's very simple, even for large n. So this can be computed easily in, say, log n time. So meaning computed, not just easily, but fast. That's the point. In log n time, by first computing inductively 2 to the k times P, which is 2 to the k minus 1 times P plus 2 to the k minus 1 times P, and using a binary expansion of n. So that's fast. However, the opposite problem, so if I know what n times P is, but don't know n, then it's pretty much impossible to find out n, not just because it's not well defined. I mean, there will be many numbers n satisfying that, because after all, I mean, we're computing in a finite group, say over a finite field, so there will be several n satisfying that, but not even finding one is feasible in reasonable time. However, given P and Q, well, like P is fixed, so that means given Q, such that, well, given Q in F, it is very complicated to compute a natural number n such that Q is n times P. So I cannot sort of divide that by P or something. And so that means we have an operation, and that's pretty much the idea of any crypto system nowadays, of any asymmetric crypto system, that one has a certain algorithm, a certain procedure that's easy one way and hard the other way. And in this case, it's that, right? So to multiply P by n is easy, but somehow to divide that by P is hard. And that is not a very complicated, essentially just means there's no algorithm known to do that. I mean, people have looked at possible ways of attacking that, and then they found probably that certain values of the field and the curve are maybe bad, so then there are side ways around that. But in general, if you pick this nicely enough, then there's no other known way than just brute force, right? You just start from n running 1, 2, 3 and checking once you get P, right? So that means there's no algorithm known. And that means there's only brute force trying all n. And of course, if n has, then think of an n having like hundreds of digits or so, then you can't do that, right? You can still do A, but you cannot do B. So that's a classical example of a one-way function, right, as it's usually called. So you can multiply n by P, but you can't divide it. And that's the idea, and that can be now used quite easily for cryptography as follows. So Alice and Bob, they both pick a secret number, a large secret number. So say Alice picks the secret number, natural number, and computes n times p. And she will make this public. And Bob will do the same. Bob also picks a secret number m and computes m times p and makes this public. And the point is now that both can compute m times n times p. Because Alice knows n, a secret number, and she knows m times p. This has to multiply, get n times p. And Bob the same way. Bob knows m and knows n times p and can compute the same as well. But anybody else having not n and m and only these n times p, m times p, cannot reproduce what n and m is, and there's no way to get n times p from these points and all those data. So then, both Alice and Bob can compute. So in terms of Alice, it would be n dot, then in brackets, m dot p. And for Bob, it would be m dot in brackets n dot p, but it will be the same as it's a group structure. But nobody else can. And so the idea is just to use that point as a key, as a secret key for communication. So it's some random point. But the important point is that they both know it and nobody else does, so they can use that for ordinary cryptography. They can now use this point, which of course always means like the coordinates of that point, right? So to get numbers, and use this point as a key for ordinary cryptography. Means for symmetric cryptography. For example, just add this number and take it modulo something else. Right? And if you both have the key, you can reproduce it. Otherwise, you cannot. So that is the standard, as I say, if you log into some website, that's exactly what you want, right? So you want to be able to communicate with the website so that nobody else can hear what you're doing. And that's exactly what works with that. And so just as a remark, so as I said, so this is actually used in practice. In many applications. And so say websites, messengers, whatever. And mostly with the following data. So as I said, they pretty much all, or many of them, just use the same data even. And that's a crypto system that's used. So if you can Google that in Wikipedia, you'll find an entry for that. That's curve 25519. And the reason is because like the ground field is, so for K, you take z mod pz, or the prime number 2 to the 255 minus 19. That's a very, very large number, but a prime number, as one can show. And so the curve f, you can also find this on the web page. So as I said, they're all using the same curve, the following: y squared z minus x cubed minus some weird number, so 4a662 x squared z minus x z squared. So as I said, the reason why they pick a particular one is that you want to make sure that some attacks that might be possible if you pick special values should not be possible, and then they try to do some research which ones are nicest for that, and that's the one what they take. Then the base point P0 is actually the point 0, 1, 0, which hopefully lies on that. So if x is 0 and z is 0, then this is all 0. So take so that is the point. So if you draw a picture of that as if it was a real curve, then that's actually the point at infinity. So for computations, one often takes the point at infinity for the base point because it's easier to compute with that. Then lines through P0 will just be vertical lines. And for example, minus P is just the reflected point on the x-axis and so on. Right? So this curve also has a symmetry. And for the point P, one takes, so one point doesn't matter, we take, but it is the point with x coordinate 9, just the number 9. And so then you can compute y from that. So z is 1 in the affine picture. So then you can compute y, and there's two possible values. You just pick one of them. And they all use this same data. So that's readily implemented on a computer as a crypto system, and it uses exactly this thing. And so that, I think, is very nice that you can use, I mean, also this theory of plane curves for cryptography, and that not just in theory, but it is actually used all over the place in the internet. Yeah, so that's why, as I said, so if you go to a cryptography class, you clearly hear about that. So there's not many ways around that. Yeah, so I guess, but the time is up. So is there any more questions? And I'll stop there for today, and we'll continue with these elliptic curves a little bit in other directions than in the next lecture. Okay.